Welcome to Science After Dark. Today's episode explores a quiet law governing every star, every living cell, and every passing moment. The universe can move from order toward disorder, but it never seems to travel naturally in reverse.
It is a beautiful, haunting realization, isn't it? Just taking a moment to sit with that idea.
Yeah, it really is. I mean, if you were to watch a glass slip from a table, just falling through the air in slow motion and shattering into 1,000 crystalline fragments across a concrete floor, you would know without a single doubt that time was moving forward.
You absolutely would, because in the forward direction, that is just the familiar grounding physics of our everyday lives. The glass falls, the structure yields.
And the energy disperses.
Exactly. But if you were to see that exact same imagery played in reverse, you would recognize it instantly as an impossibility.
Yeah, the idea of chaotic, scattered shards suddenly trembling, rising from the floor, and seamlessly fusing back together into a pristine glass, I mean, it feels like magic.
It does. It breaks the fundamental intuition we hold about how the world operates. And yet, if we were to look much closer, down past the cracks in the glass.
Down to the microscopic level.
Yes, down into the silent microscopic spaces where individual atoms dance and collide. Down there, the microscopic rules of the universe do not seem to care about the past or the future at all.
Wait, really? They don't care at all?
Not inherently, no. That is the profound paradox resting at the heart of modern physics. At the most fundamental level, the equations of motion are perfectly time-symmetric.
So they work the same either way.
Precisely. If you watch two atoms drift toward one another, collide, and bounce away, that sequence looks perfectly valid whether it is played forward or backward.
Wow. So the fundamental forces of nature do not actually possess an inherent one-way arrow.
They do not. But when you zoom back out to our macroscopic world, the world of falling glasses, of breaking waves, of living and dying, suddenly time has this unmistakable, relentless forward momentum.
So if the microscopic rules of the universe don't care about past or future, where does this relentless forward momentum come from?
To find that answer, we have to drift into the quiet, mathematical spaces of classical thermodynamics. We have to redefine a concept that is, well, often deeply misunderstood. We must look at entropy.
Entropy. People usually just equate that with chaos, right? Like a messy bedroom.
They do, yes. We often use the word messy to describe it, but entropy is not simply a measure of visual chaos. To truly understand why a glass shatters but never unshatters, we must view the world as the physicist Ludwig Boltzmann did.
Back in the late 19th century, right?
Yes. He realized that entropy is fundamentally a measure of probability. It is about counting the sheer number of possible microscopic arrangements, what he gently termed microstates, that result in the exact same macroscopic reality.
So it is less about visual mess and more about the hidden mathematics of arrangement.
That is exactly it. Picture, if you will, a brand new deck of playing cards. When you slide them from the box, they rest in a state of absolute perfect order.
Right. Spades, hearts, clubs, diamonds. Ace through king.
Exactly. For the deck to exist in this perfectly ordered state, there is exactly one microscopic arrangement that satisfies the condition. But as you begin to shuffle them, as the paper softly slides and mixes, you are introducing the cards to a vast landscape of possibilities.
Because there are billions upon billions of ways for the cards to be arranged that all simply look like a shuffled deck.
Precisely. As you continue to shuffle, the deck naturally drifts from a highly improbable state toward a highly probable state.
But, well, a deck of cards is a finite human construct, isn't it?
What do you mean?
I mean, the order of suits and numbers is an artificial meaning we assign to them. Nature doesn't care about the king of hearts.
That is a very important distinction to hold on to. You are right. The analogy is imperfect because a deck of cards is static, bounded, and defined by human observation.
Right.
The universe's true deck is composed of countless shifting particles in constant natural thermodynamic motion. So instead of cards, imagine a beautiful, fragile glass bottle of perfume resting on a table.
Okay, I can picture that.
When the stopper is removed, the fragrant molecules slowly drift out. They're carried by the subtle currents of the air, spreading evenly through the room. They wander in a vast, complex geometry.
And for those millions of randomly bouncing molecules to suddenly coordinate their paths, turn around, and drift back into the tiny neck of the glass bottle at the exact same moment.
It seems like something that could never happen.
Yeah, it feels entirely impossible.
It is astronomically unlikely. But interestingly, it is not expressly forbidden by the microscopic laws of physics.
Wait, really? It isn't.
No, if every particle miraculously reversed its trajectory at the perfect speed, the perfume would retreat into the glass. But probabilistically, you could wait for 1 trillion times the current age of the universe, and you would never see it happen by sheer chance.
Wow. So that is the thermodynamic arrow of time. Entropy increases simply because there are overwhelmingly more ways for things to be dispersed than for things to be concentrated.
That is exactly the heart of it.
Though I guess to push back a little, the perfume analogy has a small flaw too, right? Because a perfume diffuses in a bounded room where molecules bounce off walls.
Ah, yes, you are completely right. The analogy eventually fails because the expanding universe has no known physical container. There are no walls for the cosmic particles to bounce off of.
Right. But the principle of dispersal still holds. Though I find myself wondering about this idea of dispersal. When we think of high entropy, we so often picture a room in total disarray.
Yes, and that is an illusion of human perception. Entropy does not dictate that everything must become visually chaotic.
It doesn't.
No. Imagine 2 rooms resting side by side in the dark. The first room looks like the aftermath of a violent storm. Furniture is overturned, books are scattered, the walls are scratched.
Sounds incredibly chaotic.
It does. But in one corner of this messy room, there is a massive block of freezing ice, and in the opposite corner, a blazing, red-hot iron stove.
Okay. And the second room?
The second room is entirely empty. The walls are smooth, the floor is swept clean, and the air is perfectly still, resting at a uniform, lukewarm temperature from floor to ceiling.
I mean, intuitively, the messy room feels like it should have higher entropy.
It feels that way, but the truth is the exact opposite. The pristine, empty room has the higher entropy.
Wait, really? The empty one?
Yes, because entropy is intimately bound to how energy is distributed. In the visually messy room, the energy is highly concentrated. The extreme cold is segregated from the extreme heat.
Oh, I see. So the energy is not yet dispersed.
Exactly. But in the empty, lukewarm room, the energy has finished its journey. It is perfectly uniformly blended. It has reached its most probable dispersed state.
But if the universe inherently drifts toward these highly probable, blended, disposed states, how does anything complex or beautiful happen at all?
How do you mean?
I mean, how do we have shifting weather or burning stars or complex life if everything just wants to become lukewarm and still?
It is because we are not yet in that empty, lukewarm room. We live in a universe of differences. Every useful process you can imagine. The softest evening breeze, the slow beating of a heart, the fierce fusion inside a star. Every single one of them depends on an energy difference.
Little temperature gradient.
Precisely. Things happen, events unfold, and life breathes specifically because energy is in the process of moving from a concentrated state down into a dispersed state.
Like a river winding its way down a mountain.
Yes, exactly like that. Imagine a river flowing with quiet power down a steep incline. While the water falls, its energy can be hardest.
Right. It can turn a wooden wheel or carve canyons out of solid stone. Work can be done.
Exactly. But eventually, the water reaches the vast, flat expanse of the ocean. It settles at sea level. The water is still there. The energy it carried hasn't vanished from existence, but it has become evenly distributed.
It has reached equilibrium.
Right. The river stops flowing and the wooden wheel falls still. Or think of a simple battery.
Okay, a battery.
The small, concentrated difference in chemical charge between its 2 terminals is what allows a flashlight to pierce the dark. But once that stored energy is evenly distributed inside the casing, the battery goes cold and silent. It becomes useless.
But if we look at the natural world, a river on Earth doesn't just stop forever. The sun warms the ocean, the water evaporates into mist, it gathers into clouds, and it rains back down.
Yes, the water cycle.
And a battery can always be placed on a charger.
You are looking for the mechanism of renewal. And on Earth, you are right to see it. But those analogies contain a gentle flaw when applied to the cosmos as a whole.
Because there is no outside to the universe.
Exactly. A river is pumped back up because it relies on the immense external heat of our sun. A battery is revived because we plug it into the electrical grid of a city.
But if you step back and view the entire boundless universe as a single isolated system, there is no external sun to evaporate the cosmic river.
No. There is no celestial wall outlet to recharge the universe's battery. In the grandest view, the usable energy of the cosmos is gradually, irreversibly unspooling, dispersing out into the dark as ambient, unusable heat.
But right now, you and I are speaking. Millions of people are breathing, sleeping, dreaming, Forests are growing and humanity is building complex technology. Aren't we creating order out of the chaos?
It is a beautiful thought, and locally it is entirely true. Local order can and does increase. A seed can draw elements from the dirt and air to build a towering, majestic redwood tree.
Right. That feels like a massive increase in order.
It is, but the uncompromising ledger of thermodynamics demands a payment. The local order of the tree can only increase if a much greater amount of entropy is produced elsewhere to pay the debt.
How does that look, practically speaking?
Return to the image of the river. Imagine a small, elegant whirlpool forming in the rushing current. The whirlpool is a magnificent expression of temporary order. It maintains a distinct, spiraling structure amidst the chaotic flow.
But I suppose that whirlpool only exists by violently increasing the disorder of the water rushing around and through its center.
Precisely. The friction it generates against the water, the subtle heat it releases into the stones below, the whirlpool actually produces more total entropy than if the river had just flowed smoothly on.
Wow.
Yeah.
And crucially, the whirlpool relies entirely on an external current of water to sustain its delicate shape.
Yes, just as we rely entirely on the low entropy light of the sun pouring down upon the earth.
So life itself is just a temporary spiraling whirlpool in the river of time.
We are. The structure of a cell, the architecture of a brain, the glowing grids of our cities, we are localized pockets of breathtaking order.
Does that mean we are somehow accelerating the death of the universe?
No, we must be careful with that phrasing. We must remember that breathing, thinking, and building do not accelerate the death of the universe in some malicious, destructive sense. We are not breaking the cosmos, we are simply participating in it.
Just playing our part.
Exactly. All physical activity, even the rustling of leaves or the reading of a book, simply plays a part in the natural, graceful conversion of concentrated, usable energy into more dispersed forms.
But if every action leaves a trace, and the universe is constantly winding down, shedding its concentrated energy, then logic quietly suggests that in the deepest past, it must have been wound up incredibly tight.
You are drifting into the waters of what physicists call the past hypothesis. And it is the most profound, lingering mystery of why time has an arrow.
So the early universe must have had very low entropy.
Exactly. The only reason your coffee cools, the only reason a river flows is because the universe began in a state of unusually, almost unfathomably low entropy, some 13.8 billion years ago. We are, in a very real sense, still coasting on the unspooling energy of that ancient, pristine concentration.
But if we look back to the moment shortly after the Big Bang, the universe is often described as a vast, smooth, uniform cloud of incredibly hot plasma.
It is.
And yet, we just established with the empty room analogy that a uniform, thoroughly mixed state is a state of maximum entropy. How can the early universe be both perfectly smooth and incredibly low entropy?
That is a wonderful, complex question. It is a paradox that puzzled many great minds. The invisible hand that changes the rules here is gravity.
Gravity, how so?
If you have a box of gas resting on a table, a smooth, uniform spread is indeed its highest entropy state. It has reached equilibrium. But the universe is a theater dominated by gravity. And for a massive gravitational system, a smooth, uniform cloud of gas is a state of immense coiled potential. It is highly unstable.
Because gravity desires to pull things together. It wants matter to clump, to ignite into stars, to collapse.
Exactly. Under the heavy pull of gravity, a messy, high-entropy state does not look like a smooth cloud. If gravity were allowed to completely run its course, pulling everything into its most probable disordered state, the matter of the universe would eventually collapse into black holes.
Ah, I see. So black holes represent the maximum entropy state of our cosmos.
Yes. So the fact that the early universe was a smooth, rapidly expanding cloud meant it was unimaginably far from equilibrium. It had a massive expanse of thermodynamic room to evolve, to structure itself, to form the galaxies we see tonight.
It is almost as if the universe began as an extraordinarily unlikely starting position in a cosmic lottery.
Yes, that is a beautiful way to frame it. A state of such pristine concentration that we are still living off its dividends billions of years later.
But you know, a lottery implies someone drew a ticket. It implies a larger system where someone or something drew a number from a set of pre-existing options.
And this is where the equations quietly fade into the unknown. Physics still cannot fully explain why the universe began in this specific, highly ordered state.
Is just a given.
Yes. The second law of thermodynamics governs how the universe behaves after the clock starts ticking, but it stands silent on the origin of the clock itself. It remains a profound mystery.
I suppose we might need new physics to understand that.
Perhaps. Perhaps the answer lies hidden in the untested mathematics of quantum gravity. Or perhaps in the sprawling theories of a multiverse, where countless cosmos bubble into existence, and we simply find ourselves in one of the rare, low-entropy realms capable of supporting the gentle flow of time.
That is a haunting thought. But tell me, does this flow, this unwinding of the cosmic spring, does it also dictate the inner workings of our own minds?
It does. It dictates the very nature of memory and experience. Because entropy is not just the physical scaffolding of the stars, it is the currency of information.
Information?
Yes. In the quiet depths of the 20th century, physicists realized that entropy is fundamentally intertwined with complexity, memory, and life. When entropy is high, uncertainty is high. When entropy is low, we possess information.
Can you give an example?
Think of walking along a silent, moonlit beach.
Okay, I am there.
The smooth, undisturbed sand is waiting. As your foot presses down, it does physical work. It compresses the grains, pushes the earth aside, and leaves a trace, a footprint.
Right, a memory of my passing.
Exactly. But doing that physical work requires energy. And in doing so, it dissipates a tiny amount of invisible heat out into the cool night air. The total entropy of the universe must increase to leave that footprint behind.
So we can remember the past because the universe is moving from an ordered state to a disordered one, leaving physical traces in its wake.
Exactly. Whether it is a mark in the sand or the delicate formation of a neural pathway in a sleeping brain, memory has a physical, thermodynamic cost.
That makes me wonder, though, what if there was a microscopic intelligence, a tiny gatekeeper, that could watch the individual particles of a system?
You are thinking of a very famous thought experiment.
Right, Maxwell's demon. What if this tiny gatekeeper could sort the hot particles from the cold ones, separating them perfectly without doing any physical work to move them? Could a mind like that cheat the system?
It is a brilliant question. James Clerk Maxwell proposed that phantom over a century and a half ago. He imagined a tiny demon controlling a microscopic trapdoor between two rooms of gas, only letting fast particles into one side and slow particles into the other.
Because by doing nothing but observing and opening a weightless door, the demon seemingly creates a temperature gradient out of thin air. It unmixes the room.
Exactly. It lowers the entropy of the universe seemingly for free.
But it cannot be free, can it?
It cannot. It took physics nearly a century to exorcise Maxwell's demon, and the answer lies precisely in the cost of information. For the demon to know which particle is fast and which is slow, it must measure them.
And it must store that information in its memory.
Yes, but a memory cannot be infinite. Eventually, to keep sorting, the demon must wipe its memory clean to make room for new observations. And the act of erasing information, the act of clearing the ledger, is an irreversible physical process.
Oh, wow. So erasing information generates heat.
It does. The thermodynamic cost of erasing the demon's memory produces more total entropy than the demon ever saved by sorting the gas. Measurement, memory, and information processing are physical acts. There is no true escape from the second law.
That is fascinating. But I suppose we must be careful not to push the physics too far. Does entropy completely explain the subjective feeling we have, that deep human feeling of time passing?
It is a wise constraint to remember. No, it does not. Entropy provides the physical scaffolding. It explains the directionality of events, why the footprint remains, why the glass shatters. But it does not completely explain the profound mystery of consciousness.
It doesn't tell us why we feel suspended in a continuous flowing present.
Exactly. The subjective experience of time is a horizon where physics softly blends into philosophy, and much remains hidden in the dark.
Let us cast our minds in the other direction, past the present moment. If we look out into the unimaginably deep future, where does this one-way street ultimately lead?
If the universe continues its quiet expansion and the gradient of entropy continues to flatten, the leading long-term scenario for our cosmos is a state known as the heat death.
Heat death. It sounds like a violent, fiery destruction.
It is a tragically misleading name. Heat death is not an apocalypse of fire and ruin. It is the absolute opposite. It is a state of near equilibrium. A slow, gentle fade into ultimate stillness.
So everything just cools down?
Yes. Trillions upon trillions of years from now, the vast stellar nurseries will empty. The great stars will exhaust their nuclear fuel, cooling into silent cinders. The galaxies will dim, drifting further and further apart in the endless dark.
And what about the black holes?
Even the black holes, the great gravitational anchors of the cosmos, will slowly leak their mass through Hawking radiation. Over a timescale so vast they defy human comprehension, they will eventually evaporate away into a thin, featureless mist of fundamental particles.
Leaving a universe resting at perfect, uniform room temperature.
Yes. The energy of the cosmos will become perfectly evenly distributed across an unimaginably vast space-time. There will be no hot patches to fuel a star, no cold patches to invite a flow of heat, no gradients left to exploit.
And without those differences in energy, no further physical work can ever be done. The universe will enter a deep, unbreakable slumber.
Yes.
But is this the absolute guaranteed end of the story?
No. We must approach the deep future with humility. Heat death is the leading long-term scenario, dictated by the thermodynamics we observe today. But it is not an absolute certainty.
What else could happen?
The true final fate of the cosmos depends on the future behavior of dark energy, which we barely understand. It depends on whether protons themselves are perfectly stable or if they eventually decay. It depends on the deeply unresolved quantum mechanics of black holes.
So there are still vast landscapes of unresolved physics that could alter the final act of the play.
There are. But if we assume sheet death is the final state, if the universe reaches a perfect equilibrium where almost nothing ever changes, it brings up an even quieter question. Does time still have a physical meaning?
Because time is measured by the changing of states, by the ticking of a clock, the falling of a glass, the flow of energy from hot to cold.
Exactly. If you strip away all events, if you are left with a universe where no energy moves, no particles interact, and no information is exchanged, time's arrow may simply dissolve. Without the flow of events, time itself might flatten out into an eternal, motionless stillness.
The thought of a quiet, fading universe, a universe winding down into eternal stillness, it feels melancholy.
It can feel that way when looking into the vastness of the dark. But I invite you to see it not as a story of destruction, but as a profound and comforting realization.
How so?
The universe's movement toward equilibrium is the very thing that breathes life into the cosmos. That relentless one-way flow of entropy, the very imbalance that ensures the future is finite, is the only reason the stars have the space to shine.
Is the reason organic matter can organize into life.
Yes. It is the reason we can form memories of the people we love and the reason any event can hold meaning at all. The fleeting, fragile nature of usable energy is precisely what gives light and life the space to exist. We are alive in the beautiful, unspooling gradient.
That is a wonderful place to leave it.
This has been Science After Dark. Rest well, and let the questions continue in the background.